Polar bears, polar cubs. We're into chapter 4. So, with chapter 4, we're going to start out by talking about the duality of light. What does duality mean? Well, it means that light can act like a particle and it can also act like a wave. It acts like a particle in the fact that it's able to shoot off other particles from atoms and things like that in the form of solar panels. It acts like a wave because if you notice in this drawing over here, light bends around corners and it wouldn't bend unless it acted like waves. So light is kind of special in the fact that it acts like a wave when it comes to electromagnetic radiation, and then it acts like a particle in the photoelectric effect. And the photoelectric effect is what explains solar panels. So I want you to be very familiar with the EMS, okay? And what the EMS is the electromagnetic spectrum. And this is all forms of light. So I know that you know that we only see this very small portion of light. However, there's gamma rays, which in the comic or movies cause the Green Hulk or the Incredible Hulk to become, massive and be able to mutate. There's X-rays that a lot of us have had in our lifetime, and they allow us to look at bones and see if they're fractured or formed in a bad way. And then we have ultraviolet light or ultraviolet rays. We protect ourselves by using sunscreen and making sure that our cells, our skin cells at least, aren't getting overly energetic and causing cancer or being burnt. Then we come down to our visible light. Underneath visible light, we have something called infrared rays. Those we see them glowing red. However, the waves underneath that, what we feel is heat given off. You may have a heater at home that is infrared. When we go to restaurants, infrared lamps are used to keep things warm before we get them. Microwaves, we all have microwaves probably at our house. We use them to cook things or to reheat things. Inside a microwave, what it does is actually excites the water molecules. And that's what it heats up the water molecules. And in doing so, it heats up the rest of your food. That's one of the reasons why if you ever heat up pizza or something that has bread in it, the bread is fine for a little bit, but then eventually becomes rock hard because you got rid of all the moisture. We have radio waves, FM first, and then AM. FM, this is usually why it's a little bit more powerful. You can hear it through the trees and everything like that. AM being the least powerful wave. And therefore, when you're traveling, this is one of the reasons why you're listening to the ball game on an AM radio as you're driving, and it cuts in and out. So this is a very, very important spectrum to know, and know kind of the order. Know what's more energetic than visible, so gamma rays, X-rays, and ultraviolet, and know what's less energetic, which would be infrared, microwaves, and then both sets of radio waves. Our next equation that we're going to use is based off of the speed of light. Well, the speed of light is constant. Okay, it's on the back of your periodic table. It is c, and with c, it's within a vacuum. So you might go, Mr. A, like a vacuum cleaner? No, not a vacuum cleaner. Inside of a vacuum, meaning that there are no particles for it to run into. It can just travel. So this is a known when it comes to the vacuum speed. But outside of a vacuum, we just use that same speed because you'd have to have instruments to know at that exact point. Inside of the equation, there are two things. So we have C equals lambda, and then it's just wavelength is nu. It looks like a V. It's kind of fancy. The distance on this, so a wavelength is from like peak to peak or valley to valley. And then a frequency is the number of waves that pass a thing in a given amount of time. So usually it's like 1/seconds, which then they made into hertz. So when thinking about it, this is constant. So as one goes up, the other one must go down, meaning that they are inversely proportional. So here's that equation that I was showing you. C equals lambda nu. The speed of light is always going to be 3.00 times 10 to the 8th. We don't take that for sig figs. In wavelengths, we must convert them to meters. Okay, because this is in meters per second. And then frequency for hertz is 1/seconds or hertz. Either one would be acceptable. And when talking about the relationship, we have an indirect or inverse when it comes to the wavelength and then the frequency. As one goes up, the other must go down because C is always going to be constant. All right, now let's try a problem. So in this problem, they give us a frequency. So they give us a nu, which is 2.63 times 10 to the 16th hertz. And then our constant would be C equals 3.00 times 10 to the 8th meters per second. Now, what are they trying to have us find? They're trying to have us find the wavelength, which is lambda, and the unit on there is going to be meters. E for the equation, we're going to use initially C equals lambda nu. However, we're trying to find lambda, so we need to divide each side by nu. Cancel out. And so we have lambda is equal to C, which is 3.00 times 10 to the 8th. And that's meters over seconds over 2.63 times 10 to the 16th hertz. Perform this in your calculator. So you take 3.00, and I'm going to do it so that I'm not really putting in the exponents or anything like that. So I'm just going to take 3.00 divided by 2.63. And I'm going to get a wavelength of 1 point now, sig figs, based off of that. That's 3. 1.14 times 10. With exponents, we subtract, so 8 minus 16 is going to be negative 8 meters. And we just solved our first problem. Now, that was light as a wave. So what happens if it's a particle? Well, light is a particle. It's something called a photon. They have no mass, okay? But they come down, they hit pieces of metal, and they excite electrons to the point that they shoot off, and they want to go someplace. So what we've done as humans, we found that if you take a metal surface and you allow it to get sunlight, and then it ejects these electrons, so you can capture these electrons and create a current and create energy that way. And that's how we got solar energy. In order to do this, you have an equation of E for energy is equal to H, which is Planck's constant, and then nu again, the frequency. So here is our second equation for this part, and that would be E equals H V, or nu, where E is going to be in energy, which is joules. Yes, look at how it is spelled. And then you have Planck's constant. Now, see this JS? That's not what stands for joules. This stands for joules times seconds, really. Okay. And again, it's constant, so it's not, does not touch our sig figs. And then finally, nu again, which is frequency. It's either hertz or 1/seconds. When it comes to a quantum, that's the minimum amount of energy that can be lost or gained by an atom. Quanta is plural. When it comes to a photon, it's a particle of electromagnetic radiation having zero mass, but holding a quantum of energy. So let's go ahead and let's move on. The photoelectric effect, pretty much what it's saying is, hey, we can absorb electromagnetic radiation in whole number of photons. It's not like we're going to be able to hold a half a photon. And because photons have quantum, they have the minimum amount of energy, then an electron will be able to be excited enough to get ejected from a piece of metal. Just a little fun fact, that speed can travel around the Earth 7 times per second. It's pretty quick. I'm still quicker. So let's go ahead and let's throw some numbers into E equals H nu. In this one, we're given the energy. So we're given E is equal to 2.02 times 10 to the negative 23rd joules. H is a constant. If you go back, you can find it. It's also on the back of your periodic table. And that constant is 6.626 times 10 to the negative 34th. So 6.626 times 10 to the negative 34th. And that is joules times seconds. Look at that and realize that it is not Avogadro's number. Please do not confuse the two. If you're having some issues, just go ahead and look at the back of the periodic table. In the upper portion, there is a box that has all the constants that we use within the class. Our unknown is going to be the nu. That is going to be in, since it's frequency, it's going to be in hertz. The equation that we'll initially start with is E equals H nu. You're going to divide each side by H, giving us the equation to just plug and chug. Nu is equal to, so we put E over top, that is 2.02 times 10 to the negative 23rd, all over 6.626 times 10 to the negative 34th. Go ahead and let's plug this into our calculators. So I'm going to put 2.02 divided by 6.626, giving me an answer of 0.3048 times 10 to the, well, it's negative 23 minus negative 34, so it becomes negative 23 plus 34, giving us a positive 11. We're going to go ahead and move this decimal place back one, and we're going to have to round at the 4. So 3.05 times 10 to the 10th, and that will be hertz. Now, that was, again, just using one of the equations. Now, something that could occur, and I bet will probably occur, is that you're going to have to use both and determine some stuff. So the first thing that you can do is you can take the energy and you can find the frequency, which is the nu, and then you can actually take that frequency and plug it in and calculate the wavelength. So that's what we're going to do here. And what we're going to actually do is we're going to see what color it's going to be. So we're going to find the wavelength, and then you should be able to look at a chart or a nice little diagram and see what color it is. So we'll start, and we'll have 3.2 times 10 to the negative 19th. It's going to be equal to E. And then you have 6.626 times 10 to the negative 34th, and that is H. Again, we're going to try to find nu, hertz. E equals H nu. Divide each side by H. Go ahead and plug it in. That's negative 34. And let's solve that. So again, I'm going to just put 3.2 divided by 6.626. Get that answer. Know that I'm going to have to move the decimal place to the right one, and I can only have 2 sig figs. So I'm going to get 4.8 times 10 to the, let's see, it's already negative 1. So a negative and a negative makes it plus 19 plus negative 19 plus 34. That's 15. So this would be 14 hertz. Now comes the next part. Now we're going to take this, and this becomes our given. So the other given that we would have is 3.00 times 10 to the 8th meters per second. Again, that constant is found on the back of the periodic table. We're going to try to find the wavelength in meters. C is equal to lambda nu. If we're trying to find lambda, we're going to divide each side by nu. Giving us lambda is equal to, so C is going to go up top. It's going to be 3.00 times 10 to the 8th all over 4.8 times 10 to the 14th. Lambda's answer then, take 3.00 divided by 4.8, and we're going to get 6.25. That's going to be with a times 10 to the negative first, but we still have to add these exponents to it. So 8 minus 14 is going to be negative 6, plus a negative 1 becomes times 10 to the negative 7th meters. Now, on the charts, when it comes to them showing the color, they can show color in the nanometers. I want you to understand that nanometers is 10 to the negative 9th. So what happens is this moves back 2 places, becomes 10 to the negative 9th, and you get 600. This is equivalent to 625 nanometers. So let's see what color calcium has. So looking at this chart at the top, you 625, here's 600, here's 650, so dead middle. That's going to kind of be a yellowish orange, or, pretty close to orange. So our calcium has an orange flame with a little yellow. This is the spectrum for hydrogen. So hydrogen can actually have a give off different light. You can see that it gives off 4 different lights, and then the rest of the lights down here on the bottom are what it absorbs in order to produce those lights. Okay, the larger jumps equal lower wavelengths, and who would be jumping? So when we say who is jumping, electrons are jumping. And what this is asking us is talking about ground states. So that's the state in which they normally stay in. That is the lowest. Okay, if you guys were able to, you'd stay at home and be in your PJs all day, probably, just kind of lounging on the couch. Excited state is where it reaches the higher potential energy, and then eventually it will want to jump back down. When something goes from a ground state to an excited state, so when it goes to the excited state, we're absorbing energy. However, it's when it returns back to ground that it gives off energy, and that is in the form of light. So when it goes to the ground state, from the ground state to the excited, we're absorbing, nothing occurs. We don't see anything. It just gets bumped up. However, when the excited state electron jumps back down to its ground state, it has to give off some energy, and it gives that off in the form of light. So spectrums are really nice. They can tell us a lot about elements, and each element has its own special absorption and emission spectrum. Based off of hydrogen, okay, we get the Roy G. Biv, great American right here. Okay, I hope everybody knows who Roy G. Biv is. And then you can tell that it needs a lot more energy. So this is a lot more energy given off because it's more steps than this one. So again, just another way to see it, and we'll see it in another way, and even another way. Higher energy given off gives more energy off. So what I mean by that is if you go from 1 to 2, there's not much energy that you had to absorb, and there's not going to be much energy to give off. However, if you go from 1 to 3, notice how big of a jump you had to make, meaning you need a lot of energy to do that, and therefore you're going to give off a lot of energy as well. Okay, this shows absorption, and this shows emission. And then finally, you can kind of see, think about it as like almost like plateaus you're jumping up, not one flat ground or anything like that. You're really jumping up to something. So as it comes down from 3 to 2, it may give off color, it may not. It just depends on how much energy really is in that distance. Usually it needs to jump a pretty big jump. Like 1 to 2 is harder than 2 to 3, and part of that has to do with the electrons becoming further and further from the nucleus, meaning that there's not as much hold from the protons. So if I were to move from 3 to 2, okay, are we gaining or losing energy? We're going to be losing energy because we're moving back towards our ground state. That means if we're losing energy, that we are emitting energy. And then would it allow light to be seen? Depends on the amount of energy. All right, polar bears and polar cubs, that's been 4.1. I hope you learned something new, and go ahead and apply those two mathematical equations to your homework worksheet. All right, if you have any questions, just